Okay, so in this video now, we want to look at power sets, and our goal here is to show that there are sort of a plenitude of different sizes of infinity, because at this point I've shown you how to compute the cardinality of sets using bijections. We've played around with the fact that the natural numbers are countable and the real numbers are uncountable. And now we want to see that there are various different sizes of uncountable sets. So that's going to use the power set. And the power set is very important in set theory. It's involved in one of the axioms of Zermelo-Fraenkel set theory. So, but first, let's just kind of start with simple things and define what the power set is and play around just with finite sets for a little bit. And so if A is a set, then the power set of A, which is denoted by, do this like little curly P. It can be different in other places. Usually some kind of fancy P is the set of all subsets of A. Okay, so that's the definition. Great. Again, this gets used a lot in set theory, so it's a very important thing to be familiar with for set theory. For us, we're going to use it to, again, exhibit that there are a hierarchy of different sizes of sets of uncountable sets. But let's start with something really down to earth. So let's just say A is the set containing 3 elements. Okay, great. So now we want to just compute the power set of A. Okay, well, it's a set of all subsets, right? So first of all, the empty set is a subset. There is the singleton, so the set containing 1, the set containing 2, the set containing 3. Okay, and then there's the sets with 2 elements. So there's the set containing 1 and 2. There's the set containing 1 and 3. And there's the set containing 2 and 3. And then, of course, there's the entire set itself. And that's the entire power set. That's the set of all subsets that you can have of this set, right? So it's finite, it only has 3 elements, so this isn't too bad. And let's just notice that the cardinality of A is 3, and the cardinality of the power set of A, if you count it up, it should be 8, which you should notice is 2 to the 3, 2 to the size of the set A. Okay, so let me just write it that way as well. 2 to the cardinality of A. That will be important for later, but for now, let's just write it as an observation. Okay. All right. Let's step up a little bit here. Though I'm going to regret this a little bit probably, because it gets much harder to write down all the subsets eventually. But let's go for one more example. So let's say A is the set 1, 2, 3, and 4. And now I want to write down the power set of A. Okay, well, it's easy to start out. You get the empty set, you get the set containing 1, the set containing 2, the set containing 3, the set containing 4, and that's it of the singletons, right? And now I got to start listing off all the 2 element sets. So there's 1 and 2, 1 and 3, and 1 and 4. Okay, and then there's 2 and 3, and 2 and 4, and then there's 3 and 4. Okay, that should be all the 2 element sets, and now we need to go to the 3 element set. So there's 1, 2, and 3. There is 1, 2, and 4, and then there is 1, 3, and 4. and then there's 2, 3, and 4. And let's see, am I missing something? Probably. Let's see, how many sets we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, I'm good. So then the last set is 1, 2, 3, and 4. And I'm kind of cheating because I already know what the answer is to this, but that's okay because it's also helpful to do that. And so the size of A is 4, and the size of the power set of A is, if you count like I just did, is 16, which is 2 to the 4, or 2 to the size of A. So I'll let you do this as an exercise because I don't want to write it down, but I think if you're still playing around, it's worth doing one more. So it depends. If you already understand and you feel like it's pretty clear, then don't have to do this exercise. But if you feel like you want to play around one more time, then fill this in. And you will see though that the size of A, of course, is 5, and you should find that the size of the power set of A is 2 to the 5th, so 32, which is 2 to the 5th power, or again, 2 to the size of A. So, we can make a conjecture, or we can note. So notice that when the size of A is finite, we observe that the size of the power set of A is equal to 2 to the size of A. Now, I'm not going to give a formal proof. I just want to give a rough idea. This is a combinatorics proof, or a combinatorics kind of fact, and the proof is in the flavor of a combinatorics proof. So let me just give you the idea of how to prove something like this. And so the idea is the following. Let the size of A, I don't actually have to do this, and consider the fact that each subset of A is a choice of including or not including each element of A. So consider n blank spaces. So this isn't usually the way you think about a subset per se. Usually just, I don't know how you think about a subset, but you don't usually think about it like this. But the point is that you can think about it like this. There are n blank spaces, and when you choose a subset of A, you either choose to include the first element or you don't. You choose to include the second element or you don't, the third element or you don't, so on and so forth. So for each element in the set A, you have 2 choices. And that's the key to understanding the combinatorics, right? So you can now think of like 1, 2, 3, 4, dot, 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 n blank spaces. And for each space, I have 2 choices. So there's 2 here, 2 there, 2 there, 2 there, 2 there. And so if I have 2 choices for each blank space, then I get a total of, so we get a total of 2 to the n choices of subsets of A. So it's not written in a very careful way, but it's certainly giving you the idea, and you can try to write this down more carefully if you like. But for the most part, we're not that interested in power sets of finite sets, though we can be interested in that as well, depending on what we're doing. But what we want to play around with next is power sets of infinite sets, okay? So for now, though, we've just observed this fact about power sets of finite sets. Great. So now let's just do an example where we consider the power set of the natural numbers. Now we can't write down the power set of the natural numbers. We can't write all the sets out because there's infinitely many numbers in the naturals. So then there are infinitely many subsets. So, that's not what I'm going to do here, but I just want to like remind you of some elements in the power set. So for instance, 1, 5, and 7 is an element of the power set. So any finite subset is an element of the power set, right? But also 2 times the naturals or the even naturals is an element of the power set. And also so is like some set like 1, 2, 4, 8, 16, 32, where I just take powers of 2. That's an element of the subset. And usually when I write things down, I need to like follow some pattern. So, but there's also like subsets of the naturals that don't follow a nice pattern where I just pick out, again, just you can, even though there's infinitely many slots, you can still think about it like we did up here for the finite case. For each element of the naturals, I either choose to include it or I choose not to include it, right? So you can imagine making choices that don't really seem to follow much of a pattern, but they are subsets, right? So I don't know what other subsets are worth writing down here, but there are too many subsets to list out, right? So then the question is, what is the relationship between the size of the naturals and the size of the power set of the naturals, right? Because again, for finite sets, the power set was like on the order was the size of 2 to the power of the size of the original set. That doesn't really work, or at least doesn't seem to work for infinite sets. So we need to understand now what the relationship is. So for instance, n is countable. The natural numbers are countable. Is the power set of the natural numbers countable? Is it uncountable? Can we say something about, how big it is? That's what we're going to try to do in the next video.